It's known that caffeine intake can cause a short, sudden increase in blood pressure. Suppose we wanted to study this relationship. How might we go about this? We might try interviewing a group of regular coffee drinkers. As well as measuring their blood pressure, we could also ask, how many cups of coffee did you drink this morning? If you were asked this question, do you think you'd be able to give the correct number? Suppose you'd had 3 cups of coffee. This represents the truth we are hoping to observe when we ask you about your morning. But you might forget that 3rd cup and say you only had 2. When we analyze data, we implicitly assume that the values we observe are the same as the true values we are trying to measure. In other words, if you tell me you drank 2 cups of coffee, then I'll assume that you drank exactly 2 cups, no more, no less. In reality, there's a difference between what we observe and the truth we are trying to measure. When such a difference exists, it is called measurement error. We'll see in future videos how and why measurement error can affect your analysis and what can be done about it. In this video, we're going to explore what measurement error is and the different forms it can take. The simplest and most intuitive form of measurement error could be described as classical additive measurement error. Additive error means that the value we observe is equal to the truth, plus or minus some random error, or noise. We can think of our coffee drinkers knowing roughly how much they'd had, but reporting an over or underestimate of that truth. A special case of additive error occurs if, on average, the over and underestimation balance out. For example, we might find people are equally likely to underestimate as overestimate their coffee consumption. When this occurs, we can think of our errors as balancing. This is an example of unbiased error and can sometimes be easy for us to handle. In many cases, however, our errors won't balance out so nicely. One possibility is that people may be more likely to underestimate their coffee intake than overestimate it. In this case, the underestimation will outweigh the overestimation, resulting in biased error. A common cause of biased measurement error is social desirability bias. This occurs when respondents modify their answers in the hope of being perceived more favorably by others. Perhaps aware of the perceived risks of drinking too much caffeine, our participants tweak their numbers down a little to appear more health conscious to the interviewer. Social desirability bias can also be seen in reporting of activities such as how much we eat, how much we smoke, or how much alcohol we consume. Another form of measurement error can occur if knowledge of a diagnosis affects how accurately or inaccurately data are reported. If our participants know they have elevated blood pressure, they may be aware of how coffee consumption can affect that and pay closer attention to their intake. Here, the size of the measurement error itself depends on the outcome we are investigating. Those with high blood pressure give us more accurate data. This is an example of differential error and can be especially difficult to unravel. The size of the measurement error can also be related to the quantity of what we're trying to measure. Someone who had only 1 cup may more accurately report their behavior than someone who made several trips to the coffee pot. When larger true values lead to larger errors, we may call it multiplicative error. We've seen examples that assume what we observe is equal to the truth plus or multiplied by some error for the number of cups of coffee. Recall, however, that our original research question concerned the link between caffeine intake and blood pressure. So instead of the number of cups of coffee, we might be more interested in how much caffeine each participant consumed. If 3 participants accurately reported drinking 1 cup of coffee, does this mean they each consumed the same amount of caffeine? We might assume that a standard cup of coffee contains 100 milligrams of caffeine. However, the amount of caffeine may depend on the type of coffee used, its method of preparation, and the size of the cup. Even if our participants tell us exactly how much coffee they drank, their exact caffeine consumption will vary. Instead of what we observe being equal to the truth plus or minus some error, we can think of the truth, caffeine consumption, as being equal to what we observe, a caffeine estimate based on how much coffee was drunk, plus or minus some error. In contrast to the previous examples of classical error, this is described as Bergson error. Measurement error can occur anywhere and comes in many, many forms. Think about the measurements you've taken of important variables in your studies. Were they accurate or subject to some error? Does that error fit into one of the types we discussed? We'll see in future videos the problems measurement error can cause and what we can do about it.